Hello everyone, welcome to lecture 19 of the online course on modern display technologies, flat panel displays. Today's discussion will be on liquid crystal materials properties like refractive indices and birefringence. So here's the lecture outline. We'll have a brief introduction about the role of liquid crystals in device performance. We'll discuss the refractive indices using Clausius-Moussorti and Vogt's equation. We'll see the extended Cauchy equations for wavelength independence, the three-band model that will tell us the physical origin of refractive index. We'll discuss the temperature effect using Heller approximation and 4-parameter model. And finally, we will look into the temperature gradient of the extraordinary refractive index and the ordinary refractive index and the crossover temperature. So let us first start with why liquid crystals are central to device performance. Now, which device parameter do you think is sensitive to liquid crystals material choice? You can say it's the contrast ratio, response time, operating voltage. Yes, all of these are correct, and that's the key message of this particular section. So liquid crystal material occupies only a small portion of the display or photonic device. However, it basically strongly controls the overall device performance, and the important device properties which are affected by liquid crystal materials are the contrast ratio. It depends on the birefringence, that is delta n, the difference between the refractive index in the extraordinary and the ordinary axis, the cell gap d via phase transition capital gamma, which is 2 by d into delta n over lambda. Then the next important parameter is the response time, which is proportional to gamma 1, that is the rotational viscosity. And the third one is the viewing angle, which is governed by delta n, cell gap and the compensation film design. And finally, the operating voltage, which is determined by the dielectric anisotropy delta epsilon and also the electric constant, that is KII. Okay, so K11, K1, K22, K33, those the elastic constant that we discussed earlier. So liquid crystal materials directly determine the electro-optical performance of liquid crystal based devices. The refractive indices of the liquid crystal material basically control how light is going to propagate through your device. The cell gap also plays an important role because that determines the phase delay or the phase retardation. So the key material example that will be used throughout here is 5CV, that is 4N pentyl 4' cyanobiphenyl. This is basically the hydrogen atom of the liquid crystal research. Now, when you say the important liquid crystal material parameters or properties, these include the refractive index, dielectric constant, elastic constant, viscosity, absorption, wavelength dependence, and also the temperature dependence. And already I mentioned that the refractive index anisotropy is defined as delta n, which is basically Ne minus No, and the phase retardation or the phase change can be determined by the refractive indices birefringence, okay, that is the delta n, and the cell gap, that is H. So if you know these two parameter, you can basically, you also know the operating wavelength lambda, so you can calculate the phase change delta as 2 pi delta n into H by lambda. So delta is the phase retardation. So what we understand that the refractive index and the cell gap, this basically determine the phase change that is used in amplitude or phase modulation. Now let's look into the dielectric and elastic constants. So dielectric constants basically describe how your liquid crystal molecule is going to respond to any applied electric field, whereas the elastic constant basically describe the resistance against molecular deformation. So if you take this dielectric and elastic constants together, they basically determine the threshold voltage of the liquid crystal device. Then the other parameter like viscosity, cell gap and temperature mainly determine the response time. So how quickly or how slowly your refractive index, your liquid crystal is responding to the change in the field. Absorption is another important material parameter that will affect the liquid crystal performance. So most conjugated liquid crystal compounds basically show very strong ultraviolet absorption due to the electronic transitions. Okay, so there are bands available where this UV gets absorbed. So UV absorption bands and oscillator strength basically affect refractive indices and the photostability. So in the visible region, absorption is usually found small because the electronic absorption tail that decays very rapidly. So you can safely ignore the visible region absorption for the case of liquid crystal. So that makes them again suitable for display kind of application, because here you are mainly worried about your visible range. Molecular vibration bands appear in the mid and long infrared range, and overtunes of this vibration band can extend into infrared region around 1 micrometer. So the material absorption that affects optical transmittance and power handling capability. This is especially important for liquid crystal based optical phased arrays used for high power infrared laser beam steering. So these are the important liquid crystal material parameters and the device performance that is obtained. Now let us look into the refractive indices in more details. We will look into the molecular polarizability to macroscopic index, that is the Vox equation. Okay. So here we will learn how these refractive indices arise from molecular structure. So we will basically discuss from Clausius-Mussoti to Vox equation. So let's start with Clausius-Mussoti equation that basically relates the permittivity of an isotropic material to its molecular polarizability. It basically connects the molecular scale response with the bulk dielectric response. So here is the Clausius-Mussoti relation, epsilon minus 1 over epsilon plus 2 will be equal to 4 pi by 3 into n into alpha. So what is epsilon here? That is the relative permittivity. Alpha stands for molecular polarizability and capital N tells you the molecular packing density. That means it represents the number of molecules per unit volume. Now what happens at optical frequencies? The relative permittivity is basically related to the refractive index. So we know that epsilon will be equal to n square. So if you put this in this Clausius-Mussoti relation, so you basically get the Lorentz equation. Okay, so the same equation in the optical domain becomes Lorentz equation. So this is how the equation looks like, and this equation is now basically relating the refractive index to the molecular polarizability and the molecular packing density. So you can say that Lorentz equation is mainly applicable to the isotropic optical media. Now let us see how we describe refractive indices for anisotropic liquid crystal. Now liquid crystals are basically optically anisotropic material. The uniaxial liquid crystal will have two principal refractive indices. One is called Ne, that is the extraordinary refractive index, and another is No, ordinary refractive index. So correspondingly the molecular polarizabilities are also different. You can call them alpha E and alpha O, that is polarizability along the extraordinary direction. This is along the ordinary direction. So this tells you the optical birefringence, that is delta n equals Ne minus No. So what you can say that an early model directly applied the Lorentz equation separately for each direction. So once you just focus on the extraordinary direction, apply the Lorentz equation, and then you apply again for the ordinary direction. So you get two equations, right? However, this simple directional substitution may not or it does not actually accurately match the experimental liquid crystal result. So this is where Vox model comes into picture. In 1964, Vox proposed that the internal electric field acting on a liquid crystal molecule is identical in all direction. So the internal field can be expressed as EI equals n square, the average of it, plus 2 whole thing divided by 3 into E. So what is this EI? That is the internal electric field acting on a molecule, and this capital E is basically the macroscopic electric field. And what is n squared? This is the average squared refractive index. So the average squared refractive index n square is basically NE square plus 2 NO square divided by 3, because there are two ordinary axes. So this is how you are basically averaging it out. Okay, so that's what is mentioned here. This factor of 2 is coming because there are two ordinary equivalent ordinary directions which are basically perpendicular to the optical axis, and the one along the optical axis is basically the extraordinary one. Now based on this assumption of this n square, you can write the Vogt's equation as NE or O whole square minus 1 divided by this n square averaged plus 2 will be equal to 4 pi by 3 into n alpha E or O, okay, like this. So how do you read this equation? So you can say for the extraordinary direction you just take the E extraordinary polarizability and extraordinary refractive index. For the ordinary direction you just take the NO and alpha O from this equation, right? This is how it looks like. So the key difference between Lorentz and Vogt's model. So you can see that the Lorentz model basically uses same refractive index term n square in both numerator and denominator, right? So you have n square in both numerator and denominator. In the case of Lorentz, that is here, is the same term in the numerator and denominator. However, in Vogt's model, you are basically using NE square or NO square in the numerator, and you are using the average value of n square in the denominator. So this Vogt's model basically accounts for the optical anisotropy of liquid crystals. And when you do the experiments, you will see that Vogt's model basically, this equation basically shows good agreement with the experimental refractive index data of the liquid crystal compounds and the mixture. So here is a table that summarizes this discussion, that Lorentz is for isotropic, and it's not very accurate for liquid crystal. However, Vogt's model is for anisotropic liquid crystal. Here the numerator is this, here the numerator is based on extraordinary or ordinary refractive index. Denominator is the same parameter appears in the denominator. Here it is the average refractive index squared, and then the polarizability, because it's isotropic, it only has one. Here it is extraordinary or ordinary. So the internal field is isotropic medium local field. Here internal field again considered identical in all direction. So when you do the experimental validation, Vogt's model shows better agreement for the liquid crystal cases. So it means you should use this Vogt's model. Now let us see extended Cauchy equations. That these extended Cauchy equations are the practical tool that engineers use to characterize and predict the liquid crystal refractive indices at any wavelength. So the theoretical justification from the Vogt's equation makes it rigorous but not just empirical. So this is what we are going to see now. Extended Cauchy equations for NE, NO and delta N. So wavelength dependence of the liquid crystal refractive indices, isotropic phase Cauchy equations. The refractive index in the isotropic phase is basically described by these Cauchy equations. It is given as Ni as a function of lambda equals Ai plus Bi over lambda square plus Ci over lambda to the power 4, where Ai, Bi and Ci are basically the Cauchy coefficients of the isotropic liquid crystal phase. Now in the Vogt's model, Ne and No are coupled through the average refractive index term, that is n square average, right? Now using a series expansion of the Vogt's equation, the extraordinary refractive index can be expressed as NE, which is function of lambda as well as T. Okay. So, that comes as Ni lambda plus G into S lambda square lambda star square, that is basically the effective resonance wavelength square divided by lambda square minus lambda star square. So, what is this Ni lambda? That is basically the refractive index of liquid crystal in the isotropic phase. So, here I stands for isotropic, right. G is the proportionality constant, S is the order parameter, lambda star, as I mentioned, it is the effective resonance wavelength, and lambda is the operating wavelength. So, this is for the extraordinary refractive index. Similarly, you can write the ordinary refractive index as NO lambda T will be approximately equal to Ni lambda minus G into S by 2, then you have lambda square lambda star square divided by the difference between these two. And now you know Ne and No, the difference between these two can be called the birefringence. So, if you put these equations into this one, the birefringence dispersion, that is as a function of lambda, will look like this 3G into S by 2, and then you have these terms lambda square lambda star square divided by lambda square minus lambda star square. Now, G is assumed generally insensitive to temperature. Okay. However, there are the temperature dependence is there in Ne, No, and also that will be there in delta n, and they are all coming from this order parameter S. Now, let us see the extended Cauchy model for anisotropic liquid crystals. So, in the off resonance region, that is in the visible region also, the dispersion terms can be expanded as power series up to 10 lambda to the power minus 4 term. So, combining this expression with the isotropic Cauchy equations gives Ne or O as a function of lambda can be written as A E comma O plus B E comma O over lambda square plus C E comma O over lambda to the power 4. So, this A, B and C are basically the Cauchy coefficients for the extraordinary and ordinary refractive indices. The separate equations can be written as Ne lambda AE plus BE over lambda square plus CE over lambda to the power 4, and NO lambda will be AO plus BO by lambda square plus CO by lambda to the power 4. So, these equations provide a convenient empirical model for the dispersion of anisotropic liquid crystal. So, as you can see here, in each of this refractive index equation there are basically 3 unknown coefficients. So, your refractive index measurements at 3 different wavelengths will be sufficient to basically determine these 3 Cauchy coefficients. So, once you know these A, B and C coefficients, you can find out what is Ne and No for a particular wavelength, and then it can be repeated for any other wavelength. So, once you know Ne and No, you can also find out what is delta n as a function of lambda, that will be Ne over Ne function of lambda minus No lambda. So, this you can see using the extended Cauchy equation, you can write delta n lambda will be nothing but AE minus AO plus BE minus BO over lambda square plus CE minus CO over lambda to the power 4. So, what is seen that this extended Cauchy equation provides very good agreement with the experimental data. So, what are the advantages and limitations of this extended Cauchy model? Advantages are that it fits the experimental refractive index data very accurately, it requires only 3 coefficients for each refractive index, and it is simple to use for wavelength extrapolation. So, it is useful in liquid crystal display and photonic device design. Now, all is not good, there are some limitations. The thing is, it is mainly an empirical fitting equation, right. So, it does not clearly explain the physical origin of the liquid crystal dispersion, and it also does not explicitly describe individual electronic absorption bands. So, you will see that the accuracy basically decreases near material resonances. So that brings you to the requirement of the 3-band model, where this model, 3-band model, will be able to provide better physical interpretation by considering 3 dominant electronic transition bands. So now let us look into that. So this is 3-band model used for explaining the physical origin of the liquid crystal refractive indices from electronic transitions. So this 3-band model basically provides the physical insight behind the extended Cauchy equations. While the Cauchy model is used for fitting, the 3-band model explains why Ne and NO will have the values they do and why birefringence changes with molecular structure. So let's see this 3-band model. So the major absorption bands, liquid crystal compounds mainly absorb electromagnetic radiation in the UV and infrared. Okay, so this is mainly in the UV absorption, as you can see. So this is for 5 CV, that's the liquid crystal we mentioned earlier. 3 major absorption bands that govern the liquid crystal refractive index in the UV visible region. So the first one is the lambda 0 band, that is around 120 nanometer, that is in vacuum UV. Okay, so that is basically the electronic transition from sigma to sigma star, and it contributes nearly constant background to NO. Okay, that is the refractive index NO in both cases of extraordinary and ordinary. Then you have lambda 1 band, that is close to 200, that is this one. Okay, the first one is very narrow, somewhere here. So that is basically pi to pi star transition, that is the first one. It's a strong overlapping doublet for 5 CB, and it is centered around 200. Okay, then lambda 2 band is around 282 for 5 CB. This is the second pi to pi star transition, and it extends into near UV. Okay, so the longer conjugation will give you the longer lambda 2. So here you can see the measured UV absorption. Okay, and this lambda 1 and lambda 2 bands are clearly seen. So this is the measured UV polarization spectra of 5 CB using a homogeneous quartz cell without ITO, and here you also see the parallel and the perpendicular that basically tell you the E ray, extraordinary ray, and the O ray, ordinary ray, and the middle one is basically the unpolarized light, and the sample one is basically the sample is basically 1% weight of this 5 CB dissolved in a UV transparent nematic mixture Zetellite 2359, and the cell gap is maintained as 6 micron. Temperature is set to 23 degrees centigrade, and that is where the lambda 1 is measured to be 200 nanometer and lambda 2 is 282 nanometer. So what is observed that increasing the molecular conjugation shifts the electronic band toward longer wavelengths. Now because of the molecular vibration, bands also appear in the infrared region. So fundamental CH, CN or CC vibration bands occur mainly in the mid and long IR region. The vibrational oscillator strength are approximately 2 orders of magnitude weaker as compared to the electronic transition oscillator strength. Therefore, their contribution in the birefringence is generally localized near the individual vibrational resonances. So let's look into this 3-band refractive index model. So one, we understood that the 3-band basically considers 1 sigma to sigma star transition and 2 pi to pi star transition, and this ordinary and extraordinary refractive indexes can be then represented as NEO will be equal to 1 plus G naught EO, lambda square by lambda naught square divided by lambda square minus lambda naught square, plus G1 EO, and then you have this lambda square lambda 1 square divided by lambda square minus lambda 1 square, plus G2 EO lambda square lambda 2 square divided by lambda square minus lambda 2 square. So what lambda naught, lambda 1 and lambda 2 are basically the resonance wavelength that we identified previously, and these are the oscillator strength parameters, the G parameters. So the simplified form in visible, where lambda is much longer than lambda naught, okay, so that you can see that the lambda naught term can be approximated by a constant NO or N naught, you can say. So you can bring this as a constant. So you can write NEO will be typically equal to 1 plus N naught EO, so that goes into the background, and then you have the dependency, these two terms, which is dependent on lambda 1 and lambda 2. And then at for 5 CB at temperature equal 25 degrees centigrade, you can calculate this value as 0.4618. These coefficients are given, so that allows you to obtain all the parameters. Okay, what will be your NOE and what will be your N. Okay, these are these parameters. So you can put these parameters for the ordinary and the extraordinary case, and you can get the NEO and E or O. Okay. So now let's see the 3-band versus this Cauchy extended Cauchy thing. So we understood the Cauchy is empirical, it is excellent in visible, but it fails near UV resonance, and also it is unclear in the physical meaning. So when you go to 3-band, it basically tells you the physical meaning, so it is clear and it is accurate near the resonance, and not too many unknowns for LC mixtures. So for mixture, you have to expand this 3-band into the power series, and that will basically recover the extended Cauchy as a limiting case. Now let us quickly look into the temperature effect. Here we will be discussing about the Heller approximation and the 4-parameter model for NE and NO as a function of temperature. So liquid crystal refractive indices are strongly refractive index dependent, and these are critical for projection displays, automotive and high power applications. We have seen the birefringence and the average refractive index N. Okay, so your NE is basically this average plus 2/3 into the birefringence, and NO will be the average minus 1/3 into the birefringence. So how do you calculate this average? Average is basically NE plus 2NO by 3, because there are two equally probable ordinary X's, and delta N is nothing but the difference. This will be subscript, okay, NE minus NO, that is the birefringence. Now the Heller approximation for delta NT tells you that this delta NT is basically delta NO, okay, and that is basically the one at the crystalline limit, and then you have a temperature dependent term 1 minus T by Tc to the power beta. So Tc is basically the clearing temperature, that can be in Kelvin or degree centigrade. Now this beta is the material coefficient or exponent, you can say. So it is typically ranging from 0.2 to 0.3, and it is valid when T is not so close to Tc. So what is the average refractive index temperature dependence? Typically you will see that is linear, because the average refractive index is A minus B into T. So this A and B are the empirical coefficients, as you see here, the temperature dependent density of 5 CB. Okay, it linearly decreases with the liquid crystal density, because rho is proportional to A minus BT, which also decreases with temperature. Now we will look into the 4-parameter model that describes the NE as a function of time. So you can write NE equals A minus BT, and then you can add these terms, which are basically so A and B are basically from the fitting of the average temperature as a function of time, and then you have this 2 delta N naught by 3, and then you have the temperature coefficient term. So these terms are basically coming from the fitting of delta N T. So this is a 2-stage independent fitting. So in the case of 4-parameter model, the NOT looks like this. So the difference here is that here you have 2, here it is delta NO by 3, okay, and then you have the same temperature coefficient. So the thing to remember here is that the coefficient for delta N term here is 1/3 for NO versus 2/3 for NO in the case of extraordinary refractive index, but both share the same A, B and delta n and beta. The other values are same. So what are the key observations from this temperature dependent refractive index graph? As you see for the 5 cb here, that is taken at different wavelengths, 3 different wavelengths, 546, 589 and 633. Okay, so you can see that Ne basically decreases with temperature, no initially this NO, this again subscript. Okay, so NO basically initially decreases and then it increases, so there is a slight decrease and then increase, and then they will try to converge at the, these two will converge at the Tc. So at Tc what is happening, your NO, Ne and NO, the extraordinary and ordinary are becoming equal, so you are basically getting isotropic refractive index, and this then continue decreasing linearly above Tc in the isotropic phase, and this convergence behavior basically follows directly from the order parameter S tending to 0, which happens when your temperature is tending to Tc, that is according to the Heller approximation. Now differentiating the 4 parameter model with respect to T will give you the temperature sensitivity. So the temperature gradient of Ne will be dNe by dt. So this is what you will get if you take the derivative. So you will see that the both terms are basically negative, so Ne always decreases as temperature will increase, so it's like monotonic throughout the nematic range. You can also do the same for No, take the derivative with respect to temperature. So here you see the first term is negative but the second term is positive, and also the temperature dependency is there, so it means the dNo by dt can change. So at low temperature regime, when T is much lesser than Tc, the second term contribution is significant but slowly varying. That means the B term will dominate when in that case your this will be negative, so you will get a decreasing trend. Okay. Now as the temperature decreases, the positive term will also increase. Finally, when the temperature approaches Tc, the second term will grow rapidly. Okay, so this term will grow rapidly approaching infinity, as this T minus Tc, T by Tc to the power 1 minus beta will basically tend to go as 1 minus beta into the derivative. So that means you have a very large positive value and this will become very large, and that is basically shown here. So in the intermediate level there exists no transition temperature, so you have dNo by dt equals 0. So this is basically your dNo by dt and dNe by dt, those two terms being plotted here. Okay, so there are two different types of materials involved in the calculation. Okay, so let us define this temperature as the crossover temperature T0 for NO, and to find out what is TO, you can simply solve this dNo by dt equals 0 from the temperature gradient equation of NO, and you will see that the crossover temperature is determined from dNo by dt equals 0. So at T equals Tc, you can write this. Okay, so you basically find the relationship where it will be the slope will be 0. So here in this figure it compares the temperature dependent refractive index coefficient for two mark liquid crystal mixtures. One is MLC 92000 and the other one is TL216. So what you see here, operating temperature is less than TO, both Ne and NO will basically decrease with T. That means the difference or the birefringence will change slowly. But if temperature is greater than TO, your Ne decreases but NO increases, that means your delta N decreases faster, so it will be faster than expected in the phase retardation. So the device, as a device designer, you need to ensure that the operating temperature range stays on one side of TO for predictable performance. So here you can clearly see the temperature gradient that is been plotted for Ne and NO for these two material. So the black and the gray solid lines, they represent the calculated ones, while the dashed lines are basically the ones calculated for D and E. Okay, so these are in Kelvin. So the crossover happens around 80 degree and 52 degree centigrade for these two. So that is where you can identify the T0 for these two liquid crystals. So with that, we conclude this lecture. Thank you. If you get any query, you can drop an email to this email address. Thank you.